Greg Sheldon here, your host of Metal, Steel Manufacturing and Business Pro podcast, where you learn everything about the industrial businesses that make your modern day life possible. Welcome to the episode. Today we're going to go over metallurgy. We have AJ on the show to teach us about what the basics are, why it's important, why you need to consider the materials that you're using for the products you're making, and why the industry's forgotten about, and why is it so important to our modern everyday life? I hope you enjoy the episode. Hello, everybody. Greg Sheldon here, your host of Metal, Steel Manufacturing and Business Pro podcast. Today we have the very bright and talented Alvaro Mendoza. And let me tell you, this guy, we did a pre-meeting and he's blown me away with all the stuff he knows. And I should have probably paid more attention in metallurgy class when I was there, because this guy's got so much to share. And welcome, AJ. You go by AJ, right?
I go by AJ. Thanks, Greg.
Yeah.
I always enjoy speaking about metallurgy. I'm sure everyone at the end of the episode, if they take nothing else away, will understand that I am passionate about the subject.
Well,
I can have a nice, far-ranging discussion with you.
Well, that comes across for sure. The last time we talked, and you're passionate about the science of metals. I'm passionate about the industry, and you're passionate about the details, and that's cool because I always need help in that area. So tell us sorry to interrupt you. Tell us about yourself.
No, that's what I'm here for, right? That's what metallurgists are here for, the science of metals.
Cool. So what got you into it?
I was choosing a field of engineering. I knew I wanted to be an engineer from a young age. We don't really hear about material science and metallurgy, do we? When we're hearing, we hear about civil or electrical and mechanical engineers. And I was picking from a list, and it really fascinated me. I'm sure all engineers have that story about playing with Legos. I guess I went just a step further and was trying to describe to my family what my Lego ship was made out of that made it so strong. So I think that should have been my first clue.
Absolutely, even though it's plastic.
I mean, listen, the imagination of a kid, right?
Yeah, absolutely, man. So you kind of just chose it, like a lot of us did with Lego and stuff. And so where did you went to school for it? Yeah.
I went to a school called University of Florida, down there in Gainesville, the center of the state. Stayed there for quite a while. About 9 years old, told I was having so much fun that after I got my bachelor's, I just kept on and got my master's and PhD there, focusing on metallurgy, but with the in the field of material science overall.
Okay, cool, man. So did you find some really good teachers there, or like some mentors, or?
Absolutely. I think everyone has that one teacher who kind of really impacts them, at different grade levels. In college, it was Dr. Gerhard Fuchs. He was my metals teacher, and then later my thesis advisor. Brought me into the world of metals and eventually nickel-based superalloys, which I'm sure we'll be talking more about.
Yeah.
And in the aerospace field in general. So that was kind of my introduction, and opened my eyes to the importance of metals and materials all around us. It's a foundational field that doesn't get a lot of traction, right? There are metals in everything, and at some point along the way, someone had to make a conscious choice as to which metal that was made out of, right? So
yeah, 100% agree. It's definitely, I mean, all industries utilize metal, right? And it makes our daily lives possible. And it's silly that there isn't enough focus on it. So thank you for going into it and having the passion.
I think everyone I've talked to, once they kind of put it together and say, there's a whole field for that. I understand that because I can see how important that'd be. I think everyone just kind of needs to run into that one person who will say, that's its own thing, right?
Yeah, it is. Absolutely, man. So you had some teachers, some good teachers, and then I'm guessing you probably graduated, doing quite well. What was next after that?
Well, next, find a job, right? I went from there to to work in the forging industry. Um, what was then a place called Firth Rixson Forgings, a brand new plant in Midway, Georgia. It's still there, owned by Alcoa now, Arconic, Howmet, whatever they're going by today.
Mhm.
Um, I was there for a couple of years, doing some very exciting stuff with forging, and a new site is always really exciting. A brand new facility.
Yeah.
Um, new equipment. Everyone's kind of figuring out what's going on. It's like a startup. It's a lot of work, but you feel like you're leaving your mark there.
Yeah, yeah, that's cool. Working towards something bigger, right? A bigger vision or
Yeah, yeah, exactly. It was a lot of young engineers there. Just out of school or just starting out. So there's a lot of passion, a lot of knowledge, and just a really good environment.
good. Cool, man. So in the forging, so what were they forging parts for? What or
I've worked primarily in aerospace, so structural components, rotors for aircraft, civil and military aircraft engines, mostly out of titanium and nickel-based superalloys.
okay, okay. Very good. So super alloys. So what is a super alloy?
Yeah, what makes an alloy super, right? Well, what makes an alloy super is the ability to maintain its strength up to 90% of its melting point, while also being resistant to corrosion attacks and being spun at many, many RPMs. So if you can survive in that kind of environment, like in a jet engine, then you're worthy of being called a super alloy.
Yeah, no kidding. Absolutely. So what what's the process like? So the company that you would work for, they would give you parameters like this is what's going to happen to this part. Um,
Mhm.
then you find the materials that are going to withstand that, correct? Is that how that works?
So, I mean, my work was very much on the R&D side, but in general, yeah, you're looking, material science and metallurgy it encompasses it all, kind of, right? It's choosing the right material. It's the processing. How do we get that material from something we can buy, like a billet or a bar, um, into the shape we need, whether that's forging or casting, stamping, rolling. I mean, there's a ton of operations out there. So you have your you have your lump of metal, which there's a whole nother process to get the right lump of metal to the beginning of your forming process.
Mhm.
And then at the end of that, so you have a piece that looks good, right? Um, there's all kinds of inspection procedures, dye penetrant, X-ray, ultrasonic, you name it. It's as fancy as you need. And then all kinds of post processing. This is probably where you're a little bit more familiar. Weld repair, finishing, deburring, sandblasting, right, and heat treatment, which is super important. Heat treatment's usually the secret sauce to get you to the properties you want. And then we got to test it, right? Did I make the thing I was supposed to make? Is
Yeah,
it the right dimensions? Did I hit the right properties? Are there any defects?
yeah,
Sometimes that'll send you right back to the beginning of the process or some other part of the process.
yeah.
And
So,
then
go ahead. Sorry.
if you're good enough, then you can ship it, right? Which is the goal.
Yeah, yeah. So in the heat treating, oh, there's so many questions that came through all that was okay. So the heat treating, I mean, we know that metal moves. We know it
Sure.
expands, it contracts. Um, I'm assuming that that happens after, I mean, I know it happens, but what I'm saying is, how often do you check that? And I mean, you're calculating that in the making of the product, correct? Is that the
Sure.
metallurgist job or?
Sure. I mean, there's the metallurgist, as an engineer, is kind of my experience in engineering and manufacturing is an engineer is touching all different parts of the process, right? So, um, we may get everyone works to specifications, right? No matter where you are in what industry, there's a spec, there's a blueprint, there's a drawing, there's something, and that's what you're working towards, serious requirements.
Mhm.
It's the job of the engineer and the metallurgist to sometimes interpret those requirements. How can we, with our process, get to this finished product? Sometimes the heat treatment's laid out, sometimes there's wiggle room to kind of mess with some of the properties.
Right.
How can I get to where I need to go? And usually, I found that engineering, usually, the problem solving aspect that is kind of the hallmark of the engineer, right, comes with making a lot of judgment calls. You know, did this heat treatment go well? Did did a TC fail? What happened here? And then when something happens, when invariably it does, I don't think a product's been made yet that's defect free, although we all strive for it.
Of course. Yeah.
What went wrong, and was what part of the process? How can we fix it? So the metallurgist, like any other engineer, is focused on different parts of the process. So for metallurgists, it's all the parts that are interact with the metal.
Yeah.
So I mean, it's no different. It's just we're just kind of sometimes behind the scenes because not as well known as maybe the person who designed the part, or
Right.
the part engineer who's responsible for the progress of the part through the whole process.
Okay. So would you work directly with quality control? Is that how that would work, or is that even?
Yeah,
That's after.
in my experience with engineering is that we're kind of right there in the middle of the process. So we're the to operators, to guys on the floor, we're the face of a part, right, or the process. To management, we're the people who are supposed to know what's going on with it, right? So you're kind of stuck in the middle of all this, to the testing lab, or the heat treatment supplier, right? You're the guy who they call, hey, your part fell out at heat treatment. What, here you go. So it's kind of, you're kind of in the middle and represent the part to a lot of different processes. So it's a very interesting place to be. It's always funny to talk to my colleagues. You work with the person who's doing the job on the floor, right? The person who's running the process and who knows their job in and out, and they think you have all this power, and then you talk to the manager, and well, what went wrong with this, and you got all the answers, and it's a good place to be. Sometimes it's also can be a pretty stressful place to be, but overall, I mean, I can't. I know a lot of engineers who enjoy the challenge and the problem solving aspects of that.
Yeah. Is that the same for you?
I do. A lot of my career has been in characterization and failure analysis, which is when something happens, what happened. It's a bit of a forensics investigation,
Right.
CSI metallurgy, if you will. And it's what techniques, what happened, knowing what the process is, having process knowledge is pretty invaluable in figuring out where things went wrong, or what happened.
Yeah. Okay, so you were in research and development, and so was that a lot of where this experience comes from, or what was the research and development? What did that entail? Like, was it, you're just doing research, obviously, but I mean, what was the end result? What was the goal?
Sure. Yeah, the goal is to be able to successfully forge these alloys. So we were putting in an isothermal press. Isothermal forging means that the workpiece, the thing you're forging, and the dies are at the same temperature. Requires all sorts of fancy technologies and techniques. The whole thing has to be under vacuum. It's only needed for a handful of parts. So when you're starting from the ground up, you have to understand how the materials you're trying to forge behave at these temperatures and strain rates and all these things. So my job was to characterize the material's response. How is it going to respond to these temperatures, these strain rates, the way it's forged? How's it going to, how can we heat treat it? What kind of properties are we going to get? So it's a lot of testing. It's a lot of microscopy, a lot of analysis, and any person who's run their own dissertation experiments is equipped to do this, right? That's what engineering grad school is very practical in that you're becoming the expert on some question, some specific hypothesis, and you're writing a big paper that answers that, right? So you're doing all the investigation yourself, so determining what needs to be done, how, what techniques, all that. So I was coming out with a doctorate and coming from grad school, that was right in my wheelhouse.
Yeah. So what was the biggest challenge going from school to the workplace?
Well, some things got easier. I had more funding, right, in industry, but it was less. I was less the boss, right? There, I had one boss, and that was my thesis advisor. And if I could convince him that it was the right course of action, then and I could afford it, I was ready to go. There's significantly more numbers of bosses in the industry, right?
Mm-hmm.
So,
mm-hmm.
and a little bit less, a little less appetite for long timelines.
Okay, fair enough. It's got to be profitable, right?
Yeah.
This business. Okay, cool. Well, let's jump into some of the more detailed stuff about
Sure.
Terminology. I mean, you mentioned heat treating there a minute ago.
Yep.
Or a few minutes ago. So last time we talked, we jokingly said, some people say in the industry they want to de-stress. I don't know what it was we talked about, but it was sometimes people say these things and they're not exactly accurate in what they're saying. So
yeah, I think for any person who's on the technical side, terminology is important, and I think we as engineers, we sometimes seek kind of very precise terminology for I think good reason.
Yep.
But and when we run into imprecise terminology, what we were talking about specifically was heat treatment and a stress relief is different than annealing, right? It would, as a specific heat treatment, right? The goal is different. There are some commonalities, right? You're at a lower temperature, and you're not trying to accomplish some very fancy heat treatment aims, but in stress relief, you're really just trying to, it is what it says in the tin, right? Relieve stress. There's stress in the material from thermal cycling, from let's say you're welding, right? Harken back to your first guest, right?
Yeah.
Let's say you're welding. The area around the weld cools, and there's some thermal stress there because of the difference in cooling rate. That weld might break, right, if it's under tension. By heat treating at a lower temperature than you might normally, you can allow that stress to equalize and leave a relatively stress-free microstructure.
Okay, so if you had a weldment, let's say it's made out of whatever, it doesn't really matter for this.
It really doesn't matter. There's stress relief heat treatments all around.
Yeah. So are you gonna take that weldment and throw it in the oven, assuming you have an oven big enough? I mean, are you gonna bring everything to the same temperature, or are you gonna focus on the specific section that is stressed?
I mean, you really could do either. It kind of depends on what the overall aim is, right? If you're just looking for local stress relief, yeah, you can do it. You can do it locally. You just don't want to you want to make sure to avoid the situation that got you there in the first place, right? If you heat treat something locally, are you creating another thermal gradient that creates more thermal stress?
Okay, so ideally, what would you want to do, like to get your best situation?
I mean, for a weld, I think you put the whole thing in an oven and a furnace, whatever depending on the material, and let it do a low temperature stress relief heat treatment.
Right. And what are the numbers and the timeline? Do you know
The numbers and the timeline is highly materials dependent. There's a whole industry out there of heat treaters that can, it's different for steel, it's different for titanium, it's different for aluminum, and it's a function of what's the melting point, what are there any phases or changes in the microstructure that happen at temperatures. Is there concern about a surface reaction with heat?
Right.
Titanium reacts really strongly to oxygen. So you increase the temperature, that's how you get all those pretty colors you'll see around a titanium weld, or why titanium's welded in vacuum.
Yeah.
And you're fine in steel, right? So the quick answer for stress relief is going to be a low temperature. What that low temperature is depends on
right.
It's a low temperature for long enough.
Okay.
And of course that's it's kind of a cop-out answer, but that's if you search out the information for the specific alloy you're using, I mean that's why there's a whole industry of heat treatment professionals.
Okay, fair enough. So do you think welding is a good idea? And the reason, because that's my experience, right? And I always hated welding because I'd tack something together and it would be beautiful and then I'd weld it. Do you think there's better ways to go about creating weldments?
Sure. I mean, sure. There's plenty of new techniques. There's there's additive manufacturing techniques that are very similar to welding. My thesis work dealt with one called LENS,
Okay.
laser engineered net shaping, developed at Sandia National Labs. That pretty cool process, but you can kind of do. It looks like a welded thing, but it's additive manufactured. There's friction stir welding. I don't know if you've ever heard of that.
I've heard of it. Don't know much about it.
So you take two metals, can be dissimilar metals. It's pretty popular with aluminum, and you have a rotating tip, usually something very hard like tungsten carbide or something. You spin it at 40,000 RPMs, and you zip it down this material, and it creates it creates a weld-like bond, but it's the heat affected zone is very small. It's very clean.
Mm-hmm.
They use it to make space shuttle components. This big. You can either try and roll out these massive seamless rings, or you can friction stir weld them together.
Interesting.
So I mean, a lot of these processes, we talk about them. Some of them are old, some of them are new. They're all doing the same thing, and I think there's always a place for something like welding.
Yeah.
It's a simple question, right? How can we join these two materials together? Sometimes JB Weld's the answer, right? In plastics, sometimes you need a fancy, very unique welding process.
Yeah.
It all depends on what you're trying to do and whether what's the best way to get there, right? I mean that's engineering, that's metallurgy.
Yeah.
Right. That tells you what's the roadmap to get there.
Yeah. And this is the result. Here's the stuff we have, or available on Earth.
Right.
Make it happen, right? In an efficient way. I mean, actually, that's a good question. Like, does that ever come into your world of capitalism and making things profitable and worrying about that in the manufacturing of things? Is there somebody in the process that dictates that part?
Oh, absolutely. Ask any engineer about what kind of cost reductions they're doing.
Right.
As soon as you get maybe sometimes even before, as soon as you get a process that works, the first question is, okay, but how can we make it cheaper? Things like aerospace and space technology, sometimes you need the best process no matter the cost, right? If you're trying to make a satellite that's going to go and sit in space for 10 years and operate in vacuum, you need, sometimes the material in the process is the material in the process. There's no alternative.
Yeah.
Same thing. And if you're making a commercial plane that's going to carry 200 people for 10 years with some maintenance, if you're making something in your backyard, maybe your requirements are a little bit different, right? So it's about matching what's available, what's ideally you have the right process, the right material for the right cost and application. That doesn't always work out, and that's where we see failures and things that hey, maybe we need to use a better material. Maybe we need to use something cleaner, right? So that's I'll talk about aerospace, and that's my experience. A lot of plane crashes are always tragedies. However, a lot of times there's something that's learned from it. Here in America, the NTSB or the FAA, right? They're investigating everything that happens. If a plane goes down and there's a part that failed, they're going to trace that back to the raw material. What mine did it come out of? And every process along the way. You got to keep samples for 20 years or whatever. Every piece of paper I ever signed off is record somewhere. That's what accounts for the great safety reputation.
Yeah. So the materials that your guys are ordering, I mean, how do you know what you're getting is 100% whatever you've asked for?
Sure. There's quality checks along the way. There's chemistry testing in both raw material in master alloy and finished part. I mean, there's property testing. You test mechanical properties of utensils or whatever testing is required, and that's what these specifications are about. The specifications aren't just something, a checkbox along the way, right? That's someone's determined that is the minimum bar you need to hit, whether it's this chemistry, this tensile strength, whatever it is. The specs are there for a reason, from a safety standpoint.
Okay. So what so when we get to basic metallurgy, so what are some things that you could share with let's say business owners or people coming up through, or people that think it's not important to know? What are some basic things about metallurgy that you would share with them?
Greg, this is my favorite topic. I have a whole we spoke about this the other day. I do direct consulting, but with an education side because I'm passionate about the field and the subject.
Yeah, what's the business name, man? Shout out for yourself.
Mendoza Metallurgy. MendozaMetallurgy.com. I came out of the pandemic like a lot of people, looking at things differently than I had, and I wanted to provide metallurgy assistance to people who may not have had it. I've only worked at big companies. I've only seen metallurgists working for big companies, and I thought that everyone could benefit from access to metallurgy. Not only would I want to do the work, but I also want to teach people so that they understand as well. So every class that I have is a direct result of some interaction or need that I see in industry. So the one you and I are talking about is my metallurgy executive summary, and we're gonna do a snippet of that.
Sure.
It is a class that I made for every person that I ran into in business who didn't understand what I was doing or why I was in that meeting. Whether it's someone who works in quality or on the supply side, in management, a supervisor, just people who didn't really understand what metallurgy was and how it interacted with the business itself.
Sure.
And so, it's an important discussion to have. And, I like to start off with one that always is pet peeve of metallurgists everywhere. Have you ever read an article that said there's some new space age material, spider silk or carbon nanotubes, what have you, right? That is 10 times as strong as steel and 5 times as light.
Yeah, I've heard that.
It sounds great. But the question that we don't ask that is, what does strong mean? So what is that metric? How, if I ask you, is something strong because I can bend it and it won't break? Is that strong? If I can't scratch something, is that strong? If I, like the doors on a car, if I hit it with a bat and it doesn't dent, right? Is that a strong material? You would probably say yeah to all those things. The reality is though is that each of those situations, I was talking about a different property, a different measurable property that we kind of all group under the same banner of strength.
Mhm.
We need a little bit more precision when we talk about things in the sciences. So, if I can't scratch something, it's strong, sure, but what I'm really talking about is hardness, which is a surface level thing. You might have heard of diamond is one of the hardest materials. You can scratch most anything else. Well, diamond's not a metal, and if I smash with a hammer, you might not think it's strong, but if I'm trying to scratch something else or get it scratched,
Mhm.
we would say it's strong. Those car doors that won't dent, the best, the most dent resistant ones are made of plastic, right? And
Just gonna say
that
the best ones that don't dent are the plastic, like the bumper.
yeah, and yeah, they're strong, right? But if I put plastic in an airplane engine and spin it up, right, you're going to get a puddle at the back.
Yeah.
So we talk about bending. I can take a paperclip, bend it back and forth, right? If I take a piece of glass and try and bend it,
Mhm.
this is kind of the fundamentals of material science, right? So plastics are very tough, which is that's that property we're talking about. There's toughness. I can hit it a bunch of times and it's not going to break, and until it does. Ceramics, great intention. Theoretically, you could support a car on 4 coffee cups, one on each wheel, because ceramics are great in compression.
Right.
But if I drop a ceramic mug, what happens? Right, it shatters.
Yeah.
Uh, um,
So
aluminum baseball bats, right? But
yeah.
take your keys to one, right? You're gonna scratch it all up.
Yeah. Yeah.
So it's when we talk about strength, we want something very strong. It's important to understand that there's a variety of measurable properties, things that will go on a specification. I want high toughness, or I need high hardness, right? I need a hard surface for wear resistance,
Mm-hmm.
like in a ball bearing, or I need a tough material because it's going to get banged around, like a car door,
Mm-hmm.
or I need something that has a high tensile strength because I'm going to be pulling on it, like a wire, right? Those are all different properties, and you would use different materials in each of those cases because you're moving towards trying to optimize a specific property. But if I just said I wanted a strong material, I might choose the wrong one.
Yeah. Okay, so it goes back again to you need to know the end result of what this part is doing, right? Before you
Yeah,
can make these claims.
absolutely. One of the most important parts of any design process is what we like to call material selection, right? So that's, you want to know what the final application is so that you can select the right material, and then, along the way, the right processing route, the right heat treatment, all that.
Mm-hmm.
Sometimes the material is enough, right? Sometimes it's not.
So yeah, fair. Can you give us an idea of some of the terminology, like you talked about toughness, hardness,
Sure. Yeah.
softness,
So
style, malleability? I mean, what are there layman's terminologies that people can kind of adopt?
yeah, we talk about it all the time. So toughness is the ability to resist an impact, right? I'm going to beat on something, something with impact, a car door, we talk about tank armor, or whatever it is. It's we want something that's tough.
Okay.
Strength, there are a couple. Even when we try and get more precise, tensile strength is about pulling, right? So that's divided into two. If you look at a stress strain curve, which, we don't need to get into all of it, but when you do a tensile test, you'll get a couple numbers out of it. One is the yield strength. So how far can I pull something before it yields? What we mean there is, you're switching from what we call the elastic to the plastic region. So if it's elastic, it's recoverable, right? You pull a rubber band, you stretch it, you let go, and it goes right back to shape. If I have, let's say, a piece of silly putty and I pull it, right, it'll stay in its shape.
Okay.
But once it starts that process where it no longer will snap back to shape, that's called yield. So that's the yield strength. Okay. When then there's another property, the ultimate tensile strength, or the tensile strength. It's the highest stress your material is going to see before it starts to change in dimensions. So, have you ever seen a tensile test being run? You have a.
I don't know if it's correct where they're pulling the metal apart. Is that correct?
Yeah, exactly. So, like I said, we'll return to the silly putty example. So with the tensile test, you start pulling it. If you stop at a certain point, like I said, it'll go back. There's no ultimate dimensional change to it. You pull it too far, it's going to start stretching a little bit. And at a certain point, you pull, and then you get what's called necking, where the cross section. So let's say it's a half-inch diameter, cross section for the bar you're pulling. That'll start decreasing, and you get a phenomenon called necking. And at that point, you're at the ultimate tensile strength. That's kind of the top of the curve, the highest strength. Hardness is just a measure of the local ability to resist deformation.
Okay.
Scratching, denting, very localized, whatever it is. So steels can be made very hard through a number of processes. Aluminum is soft.
Yeah.
You have a carabiner, that holds your keys. Pull it out and look at how dented it is, right? Aluminum is fairly strong in a lot of situations, like yield strength or whatever, but it's fairly soft, so the hardness is low.
Yeah. Okay.
Ductility is the ability to be pushed into different shapes. So we talked about the noble metals, gold, silver, all that stuff. They're very ductile. They're very made easily into wires. You can draw them into wires very easily, where something else you might not. Something that's more ductile, you wouldn't be able to.
Right.
So a whole host of properties that are just kind of there and all bundled together. And there's a test for each one of them and a number we can assign, which as engineers is very comforting to us.
Yeah. So here's an obvious question.
Sure.
How does all this apply to your everyday business owner, like a machine shop, fabrication shop? Like, how do you come into the picture to help advise them on material choices? And why would they need to know that?
Sure. Yeah, absolutely. And that's the question, right? Is for a lot of cases, you're gonna, you're fabricating something. You want something that is, you're gonna go for steel, right? I can weld it. It's strong enough. And that's kind of intrinsic properties, right? That's things that it's steel, so it'll do that. The kind of the difficulty comes where you have applications where you're more on the bleeding edge, or where there's something very particular you need, and maybe a better alloy would be different. So if we're talking about steels, maybe the one something keeps breaking on you. Maybe you chose a steel that has too high a carbon content, it gets too hard. You'd be better off with a mild steel, right? That is more forgiving. Or just the opposite. You need the wear resistance of something that you can harden, and you're trying to weld up a mild steel that just won't get there.
Yeah.
So material selection is a big part of that. a part that failed. Let's say, God, I have the hardest time making this, this part, or I made this part and it keeps, the customer tells me that it keeps failing. And I don't know why. That's the whole subset called failure analysis. That's looking at the application, looking at the conditions. There's things that can happen that are outside of the realm of what you intended for the part to go through.
Yeah.
I did a project in college. These guys were stamping these big parts out, and their dies were wearing out after just one forging run when they were supposed to last for a lot longer. And we did a bunch of analysis to figure out, hey, you guys are 200 degrees higher than you think you are, and you're using the wrong material. How do we find that out? You look at the microstructure and say, hey, if you're at the temperature you said you were, this phase wouldn't be here. So that's you're 200 degrees higher, and you either need to lower the temperature or you need to change your material.
Yeah.
And it's things like that. There's always going to be, there's lab tests, there's all these kind of things, and sometimes, you want your own guy there, right? You want, I want my meddler just to read the results and say, is this right? Is this, how do we turn this test result into something, actionable? These are all the things that meddlers do in a big company that needs that full time.
Mm-hmm.
I don't believe that everyone does. Your job shop, your machine shop, they don't need a meddler just full time. That's silly.
No, but it'd be nice to have you on call, right? Where if they're finding something,
that's the idea, right? Is that I think everyone should have access. But I looked around, I didn't see a lot of that, and I wanted to be that person. Take on different projects, work in different materials. That's fun. That's being able, figuring out why something went wrong, or what's the best material for this application, or if we could maybe heat treat a little differently, would it be better? I worked on another project in college. The Society of Automotive Engineers is making a dune buggy, and they needed a higher hardness on their on these bearings, and so we came up with new heat treatment, right, to get a couple more Rockwell hardness out of them.
right? So
so projects like that are a lot of fun.
Yeah. So how do you get that more hardness? Like, let's say you're dealing with, the carbon contents to the max. I mean, I guess you got to start from a new piece, right? I mean,
you look at, it's for that. It's okay. We use this, 4140 steel, right?
Right.
You go to the books. You look up, what that, there will be a common heat treatments for steel. We've been using steel for so long that things are, there's a wealth of information there. I have a book in the other room right now that I could look up whatever alloy, and every graph I could want is right there.
That's cool.
So then it's just about picking, what I want, and there's always trade-offs, of course.
Yeah.
But it's
nothing's perfect. There's no perfect material.
No, of course, but that's, hey, am I willing to accept that I'm going to get that few more Rockwell C, hardness out of it, but it may be slightly more brittle?
Right.
Is that okay?
Mm-hmm. Mm-hmm. Exactly. So when it comes to the numbers of materials, so the specifications typically is 4 numbers, right? So you got like 1018, 4041. What do each one of those numbers mean? Do you know that off the top of your head?
Yeah, sure. So again, steel's easy. Nickel-based superalloys are more difficult because every company has their own naming convention, their own thing, and then whether it's patented or not patented, I'll use a material that a lot of your listeners will probably know only as Inconel. I know it as Inconel 718. It's the most popular nickel-based superalloy. It accounts for about 50% of the market share. But you walk into a machine shop and you ask for Inconel, that's what they'll give you. but there are a number of Inconels because it's just an alloy that was made by the International Nickel Company,
Okay.
which is which yeah, Inco made Inconel alloys.
Mhm.
Now for steels, everything is fairly highly regulated and been codified at this point.
Right.
In the U.S., we go by the AISI, the American Institute of
Yeah.
American Iron and Steel Institute, or Society of Automotive Engineers, have a grading system, which is typically 4 digits. The first digit reflects the series. So 1,000 is carbon steels. The 4,000 you mentioned is a specific set of alloying additions. So let's see, the 4,000 series. If I pull out a reference,
Sure.
the 4,000 series is molybdenum steels. So 1 through 9 is that. That for that first digit all means something. The second digit is the specific designation, which is usually the presence of major alloys. So if we talk about that 4,000 series, which is all molybdenum steels, right? We mentioned 4140 earlier. That would be chrome moly steels, or as they're typically known. And then the last 2 digits are the carbon content.
Oh, okay.
With a decimal in front of it. So 4140 would be a chrome moly steel with 0.4% carbon.
0.4%. Okay. Very cool. Well, thank you. I didn't know that.
But yeah, I mean the British, the Japanese, the Europeans, everyone has their kind of has their own. But
Right.
The idea is that when you're looking for 1018 steel, no matter where you buy it, it's 1018, right? That it's got to fit a certain compositional range, a certain kind of range of properties.
Yeah.
So we're talking earlier about how do you know what you're getting. So when you order to that specification, you can test it, and it should, they should give you the test results that because they should be testing. Say,
Sure.
we did some testing for this batch of steel.
Hmm.
This is the results. It conforms to the specification. You're good to go.
Yeah. They should be. I had a guest on the last episode about he was telling me about Kobe Steel in Japan, where they've been falsifying their materials for like 40 years. It was crazy story.
Meddlers are no different. There's there's bad apples everywhere, right?
Yeah.
There was a case kind of locally here. I live in Portland, Oregon, and in Washington State, there was a metallurgist who got sentenced to federal time.
Wow.
And had to pay a huge fine because she had been falsifying steel reports for like 30 years. Unfortunately, the steel was going into nuclear submarines, so the government didn't really have a strong view of that. And there's some severe repercussions. A lot of time and labor to verify that the steel was good, and a lot of problems to fix based on that. But
Yeah.
this bad apples are everywhere, right? But
Yeah, absolutely. Well, she probably
first I'd ever seen a headline like metallurgist gets sentenced to 2.5 years in prison. That was surprising.
there's a first for everything. Yeah, they're probably just mad that they had to spend all those resources on her for something they don't think.
It was something like 50,000 man hours to go back and recheck all the subs. And it's her reasoning was it's one of those things that you're like, that's not that bad, but her reasoning was that she thought the specification was too stringent, that it was too tough to hit. It wasn't. They didn't need all that, all the right properties. And she may have been right. I don't know, but
it sounds like something
that's not. That's not the way to go about it, right? That's
Yeah.
You go back and argue with your customer about the specifications, see if you can prove that you don't need to hit the same ones. You don't falsify the records.
Exactly. I mean, it really doesn't matter what you're making. It's that integrity is important to have, especially when it's in your own country, I think. Um, I think there's a bit of a segue into, I'm curious your thoughts on the tariffs and the China steel coming into North America, and what your thoughts are on that around specifications and the whole tariffs.
Well, global trade's way to pick a doozy. Global trade's, an interesting topic. I think it's tough because for a lot of things like aluminum and steel, it's commoditized now, right?
Mhm.
There's such big, large amounts needed, and you know, every business along the chain needs steel or aluminum or something somewhere, and you know, obviously, it'd be great if every country could provide it to itself, the resources needed, but
Yeah.
the way things have shifted, and globalizing all these things, it becomes difficult. I've been lucky enough to work in aerospace where that's less of an issue because um, we have to have U.S. made materials,
We do.
right? A lot of the nickel based superalloys are ITAR restricted. They're tariff protected technologies.
Okay.
Um, so you can't go to China or Russia or sometimes even Europe for the material.
Right.
Um,
Okay. Okay. So I mean,
a
all
lot of it's made a lot
this,
of it's made in house or
so it's all
whatever.
sourced in. What if you can't get the materials you need in America?
Um, there are I'm sure there's some other recourses. I never ran into that thing, thankfully.
Okay.
I think we had some Russian titanium somewhere, but we couldn't use it for anything because no one wanted it in the material, in the part. I don't know why we bought it. That wasn't my decision.
It's probably a microphone in it or something.
It would be difficult, but um, yeah, it's really interesting. But I think got a lot of people out there who all need the same thing. And like I said, 1018 steel is 1018 steel for the most part.
Mhm.
There's some applications where you're going to want to make sure that it went through the right processing, and the right routes to get to where you are. You can get 1018 by a number of different manners, but if you need it for an application where it's defect sensitive, then there's some processing routes that will ensure that you have the cleanest product. So depending on your application, if I need mild steel for a chair, does it matter the provenance of it? No, but if I'm making the landing gear for a plane,
Mhm.
then that might make a difference, right? So like we talked, that application is important. I
Mhm.
think that kind of is part of it,
Yeah.
right? It's the material, but do I need a very fancy high strength low alloy steel for applications that a plain carbon steel will do? Probably not. Save some money.
Yeah. Cool, man. All right. So tell everybody again about your business. Where can we find you, and all that good stuff?
Sure. Yeah. Mendoza Metallurgy, of a one-man band, of a metallurgy shop. I do direct consulting, and then I have several classes, for a wide variety of experience and skill levels.
Yeah.
Um, and you can expect the same kind of enthusiasm that you're hearing now to bear on any metallurgy issue. Yeah, Greg, if you couldn't tell, I'm passionate about the
Oh,
subject, and
I can,
uh,
I can tell. Absolutely.
I,
Hey,
I like to share my knowledge and work on fun problems.
yeah. Well, I'm sorry I got to wrap it up because I got another call here in a couple minutes. But AJ, I appreciate your time, and we're gonna do this again because there's so much more to talk about. Any parting advice for anybody out there?
Yeah, I mean, I think once you start thinking about that, once recognize that metallurgy is a thing, and once you start thinking about things like what kind of strength are they talking about? I think it opens everyone's eyes to kind of the world is out there and the importance. So I would ask everyone to start thinking about things in your own life that might be metallurgically related, and see what we come up with.
Cool, man. All right. Always a pleasure, sir.
Yeah, thanks, Greg.
All right. We'll talk to you soon. Thank you.
Have a great day.
Okay, you too. Bye-bye. That wraps up the episode. Thank you very much for joining us, me and AJ. I really thoroughly enjoyed learning about metallurgy and all that time I didn't spend in class. Now I don't need to fret about that because now I know AJ. I can call him up anytime, but also this episode and the many more we're going to do has taught me a lot. So thank you, and I look forward to the next one. Greg Shelton here, your host of Metal, Steel Manufacturing and Business Pro podcast, where you learn everything about the industrial businesses that make your modern day life possible.